So the next presentation is on the Rapid Converter Framework, an approach to ultra-fast converter development. And that's going to be presented by Paul James Jones from Boehringer Ingelheim, Justin Van Duyn from Pfizer, and Bo Du, also from Pfizer.
Great, thank you very much. Can everybody hear me clearly?
Sounds great, and we can see your slides perfectly. Thanks,
Okay,
Paul.
great. I'd like to start with a little short story to set the stage. President Roosevelt had a problem. In the early 1940s, Nazi U-boats were sinking Allied shipping at a blistering pace, threatening the lifeline that was vital to sustaining England and Russia, and therefore severely jeopardizing the ability of the other allies to keep up the fight with the Nazis. Shipbuilding and converter construction is a craft process, nearly everyone bespoke. On average, it took almost a year to build a simple cargo ship. At this rate, the Allied lifeline could last only months longer. The future looked bleak indeed. Roosevelt turned to our friend Henry Kaiser for help. In the 1930s, Kaiser had built the Grand Coulee Dam when almost everybody else said that it was impossible. When the engineers said that the mountainsides were too soft and too wet to support the concrete while it was hardening, Kaiser simply froze the mountain with massive refrigeration channels. The dam still exists today. Unfortunately, Kaiser knew absolutely nothing about shipbuilding. Roosevelt would wince whenever Kaiser talked about the front and the back of a ship. As a former Secretary of the Navy and avid yachtsman, this was especially painful for Roosevelt. But Kaiser was absolutely electrified by the idea of another impossible challenge. Roosevelt famously said, "I don't care what he calls them, just as long as he delivers." And deliver he did. Within 18 months, Kaiser got the delivery time of what were ultimately called Liberty ships down from nearly a year to around 20 days per ship, and then went on to eventually set a world record at 4 days for a ship. Kaiser did it through massive simplification, standardization, and separation of the shipbuilding process into tiny basic steps that virtually anyone could execute. In short, he took the craft out of a craft process. Needless to say, the professional shipbuilders were mortified at what Kaiser did to their beloved profession. But the rest, as they say, is history. There is a lot that we can learn from Henry Kaiser. Okay, so the current state of the problem. As we've said, it applies to shipbuilding and applies to converter development as well. Converter building is currently a craft process requiring arcane knowledge and skill. It is slow precisely because it is a craft process and requires arcane knowledge. In order to move beyond the hobbyist's workshop model, we need to be inspired by Kaiser's example. Building on our collaborative framework in developing converters with Pfizer, we are laying the groundwork for a rapid converter framework that will potentially let us build brand new converters in days, not weeks or months. It is based on Kaiser's core principles: ruthless simplification, ruthless standardization, and ruthless separation into tiny elemental steps. Wherever we can, we're letting software automate the production of converters. By building and writing data models, by writing code and other software writing other code, and by testing the output. What you will see here is not necessarily the final form of the rapid converter framework that we might implement, but is intended rather to show what's possible and where we're going. So let's get started. In the beginning, there is a vendor file parser. And if you can't read the vendor file, the proprietary vendor file, then there really is no realistic chance to ever build the converter. So the assumption is that a vendor file parser is available, either through internal development or through collaboration with the vendor. So we assume that the parser is available. But once you have the vendor file parser, we can feed a piece of software that we call the data model creator to automatically build, by writing code, a minimalistic first version consensus data model for us. And it's a fully automatic process. No human intervention is required. And we've decided to standardize on CSV as a messaging format between the components of the converter framework. And this is not necessarily a final design decision. JSON is also possible. And so the next step in the process is that the data model is fed to another component we're calling the CSV creator. But before we get to that, one side benefit about putting a lot of files through to the vendor parser to build the consensus data model is that it lets you stress test the file parser against a diversity of vendor file format variations that you might reasonably expect to counter in the wild. Because even for a particular vendor file, there are subtle variations that you can see depending on instrument options, for example, that are selected, file versions, instrument software versions, etc. So not all the vendor files typically are identically lockstep the same. You will see some variation. So by running them through the consensus data model creator, this allows it to account for that variation. So once you have the consensus data model, you can start producing your first files immediately. And for the purpose of this talk, we're going to talk about ADF. The consensus data model creator writes the code that the CSV creator needs to implement the data model right away, which is compile and go. So the idea is that the CSV creator takes the data model, which was just generated, and then for any new files that come through, it takes that data and then creates ultimately a CSV file, which is reformatted to TTL, which then goes to the Flex ADF aggregator, which was developed by our colleagues at Pfizer. And this is really the heart of the whole thing, is this aggregator. And so I want to here send a big acknowledgement out to our colleagues at Pfizer, because they had this great idea of creating this aggregator software, and it really is the heart of this framework. But anyway, with this, we can now create a standard format file, again, ADF for the purposes of this discussion, with a fully populated data description. Of course, the consensus data model is the absolute bare minimum that we would need to create a standard format file. But using this consensus data model approach allows us to decouple the much slower final data model development from the converter creation. The final data model is much closer to what has been presented in other talks during this series of talks during the Connect meeting. Is again more with the vendor terms and the allotrope ontologies, etc. But by using the consensus data model and decoupling the final model creation from that, this allows our companies to get much needed near-term ROI by getting real data into standard format files, so people can poke it and prod it and get used to working with it. Again, you don't need the final data model to create ADFs. You can create ADFs from the consensus data model, which is automatically created. So an overview of the whole process is as such. Again, using the vendor file parser, we create the consensus data model, and that goes on, and then we can ultimately create ADFs. At the same time and in parallel, it's a slower process, but we can also refine that consensus data model by bringing in internal experts, for example, the folks in the circle there. We can bring in the community and get input from there. And likewise, in the blue circle, we can bring in external ontologies as well and controlled vocabulary. So by layering this on top of the consensus model, we can iteratively develop the data model that goes into the creation of the ADF files, and we can continue to improve that as time goes along. But you're not restricted by having to wait for the final data model before you can do anything. You can do anything right away. You can create ADFs right away. So what I apologize, I clicked too quickly. What it said was that the final data model was nice to have, but not required. So the CSV creator also allows us to populate the data cubes at no extra cost or effort, because one other function of the CSV creator is to create CSV files that contain the data cube information, which then goes to the aggregator from Pfizer that also goes into the ADF. Likewise, the proprietary vendor files can also be put into the data package. So summarizing the whole process, using this framework, we can go from the very beginning of having a vendor file parser to producing a standard format ADF file out the other end in less than a day. It's It's a very, very fast process. And so using flat files as a transfer medium allows us to easily intercept or modify the inter-process communication, so we can easily prototype new ideas that are not directly supported by the code base. For example, a hybrid leaf node full graph data model as an example. This ability to rapidly prototype ADF files is also useful when you don't know the best way from first principles to populate a file. You have the ability to experiment easily without having to recode. For example, peaks, do we put it in the data description or do we put it in the data cubes? Or if we wanted a second copy of the metadata, do we do that as JSON or TTL in the data package? Using this framework, we can experiment very quickly, produce ADF files, and then see if they meet our requirements in terms of downstream use. And so as a schematic, this shows how one might conceptually incorporate one of these hybrid leaf node full graph data models in an ADF file using the framework. And basically, so what you've done is you've intercepted the TTL that comes out of the CSV creator, and you would substitute the TTL that comes from some other source. And so this, again, allows you to experiment and to create ADFs in different configurations to see what's best for your needs. And so now we're going to do a live demonstration. We're going to actually build the converter. Jamie, if you could give me control, please. Okay, and can everybody see my screen?
Yes, we can.
Okay, great. Let's build a converter. And so we're going to do it from the very beginning. And so here we go. Okay, so it's compiling the file parser. It's just done that. It's just tested the file parser. Now it's creating a consensus data model. This is X-ray powered diffraction data. So here we're building a consensus model against a collection of real data. Now we capture all of the vendor metadata. We don't cherry pick those metadata values that fits into a model. Rather, we build the model around the metadata values that are actually present in the real data. In the interest of time, today we're only using a small collection of real data, around 2,000 files instead of the 200,000 or more that we would use to build models in the real world. We're looking to determine here what metadata values are present, which are required values, which are not. What are the data types of those values? Because what you find is when you look at real data, you find that even for things that are nominally integers or floating point numbers, in the real world, occasionally you can find, for whatever reason, a string value or a Boolean or something else. Knowing clearly what you might find beforehand makes the converter more robust. And so we'll just let this continue. It's going to go on for another moment. Like I said, we're scanning a series of X-ray powered diffraction files to create the consensus data model. This is almost done here. And so you can sort of see real time how this works. So this is the sort of performance that you might expect to get. And this is not a very high-end PC that this is running on. So again, we're sort of at that top step where we're pushing a large number of files through the consensus data model creator, and it's creating the data model. Okay, data model is done. Now it's just layered in the input from the expert community. That's the final data model. It's just compiled the converter. It's now running the converter on a sample data set. We're now running the Pfizer Flex ADF aggregator to create the ADF file. And this will take just about a moment. And now we're going to open it up with ADF Explorer. So we've just built a converter and then executed it. So what did we get out of that? As soon as ADF Explorer comes up, I'll show you. Okay, so let me start with the data package first. So in the data package, we have the raw data, actually the raw instrument file. We have a UXD, which is a semi-standard format for X-ray power diffraction data. And then we have a JSON file as well that we create. And I'll come back to that more in a little bit in terms of what that's all about. Likewise for the data cubes. Okay, blah, blah, blah. We have the diffraction pattern. Okay, and in the data description, we have all of the metadata that was in the original data set. So let me just pick a value. And blah, blah, blah. Okay, and immediately you see, so again, in creating the final data model, we've already put in a scope note. So this is from our internal experts in terms of what this value is. And then if we look up the instance value, you could see the actual instance value down here at the bottom, the units using the allotrope ontologies. And so what we've done here is we've recorded this metadata value. Okay, now that we've built this converter, well, what can we do with it? Well, we can convert data. So I'm going to pick this is a Brooker X-ray power diffraction data set. And again, I'm just creating the data set, the ADF file itself. I'm not rebuilding the converter because that's already done. And the other piece of it that I want to let you know is that this converter is self-contained. So the model is contained right within the converter software itself. So it's possible to distribute this and to put it wherever it needs to be able to convert data. And so we're just creating an ADF file. And again, this tool from our colleagues at Pfizer, this is very, very flexible. It allows you a lot of flexibility in terms of what you put into your ADF. Okay, so this is a Brooker X-ray data set, X-ray power diffraction data set. And again, once it comes up. And the one thing I want to show you about this one, so in contrast to the other one, which was a single experiment, this is 7 experiments in the same data set. Oh, I didn't want to do that. Sorry. I just wanted to show you the graph. This is 7 data sets in the same ADF. And although they look the same, I assure you they are different. So if you look, they are different, etc. And so again, this uses the standard aggregation pattern to represent multiple data sets in the same ADF. Okay, well that was Brooker. Let's do a different example. So this is Rigaku data using the exact same converter. So now we're using the same converter for X-ray power diffraction data from a different vendor's instrument. And so I think you can predict pretty much what you're going to see right now. So again, I won't bother to show you, but again, it has the raw data in the data package. It has a JSON file, and it has the UXD file. And likewise for the data cubes, again, it has the raw data. So it comes up here. Okay. The one other thing I wanted to show you was in the data description, for example. And this applies to all of these examples I'm showing you, but I'm just going to show you specifically for this one. Okay, let me try that again. Yeah. So what we do is we record for each of the components of the converter framework, we record an identifier, we record a timestamp when it was executed, and we record the version number. So this way, as things continue to evolve, you can easily trace for any ADF what components were used to build it. So for example, this particular consensus data model, this is the XRPD, UXD, Brooker, Stowe, Rigaku consensus data model, for example. And so this is all recorded in the data description. And so I've just given you a clue as to what the next one is going to be. So let's go for a third vendor. So there's a third vendor called Stowe, which also makes X-ray power diffraction instruments. And I think you can very well predict what you're going to see right now. So I won't go into a lot of detail here. But basically, we're running the same converter now on a third vendor platform. And again, we're capturing all of the metadata from each one of these platforms, because in the construction of the consensus data model, we included data sets from each of these vendor platforms. Okay. Okay, so I'm not going to bother to show you the data cube because you're used to seeing that right now. But one thing I will show you in the data description is not only do we capture BI specific metadata, but we capture allotrope specific metadata. So for example, what is the version of the allotrope ontology that's used in defining the units, for example. And so we can see that, and that's captured here. So it's 2020-06, which is the mid-year. Likewise, you know, if an ontology is used. So for example, in this case, you know, we can pull up, we can find out what version of the allotrope ontology was used. So in this case, we're using the 2020-03 terms from the 2020-03 X-ray diffraction model. So again, it's not just, you know, the consensus model, but when you go to the final model, you can layer in additional pieces of information. So you can make these ADFs as rich as you need to for your particular use case. Well, we've seen enough of X-ray powered diffraction. Let's look at something else. So we're going to now segue over to DSC. Again, this was a converter that was created in exactly the same way using the converter framework. And this happens to be a calibration experiment because I didn't have any non-proprietary data that I could show. So we're going to show a calibration experiment. And again, it's creating the ADF file directly from the vendor file. In this particular case, there is no allotrope component. We haven't gotten around to doing that yet. We're still collecting the input as well from our internal user community. So this is just the consensus data model. This is sort of the minimalistic consensus data model. But even with that, you can still get useful information out of it. So again, all three compartments are populated. And what I wanted to show here was, so for example, heat flow versus temperature is a common thing that people like to look at. Okay, and you say, well, what are the units of these axes? Well, that's all captured in the data description here. So even with a minimalistic model, we can still populate useful information. So, okay. So for example, if I look at what is the units for the vertical axis on that scale, I can see that it's milliwatts. And by the way, it's using the allotrope ontologies to describe that. So it's not some proprietary thing from either BI or Pfizer. We're leveraging the allotrope ontologies wherever we can. Okay, so that was DSC. Okay, we'll just do one or two more, and so this is TGA. Same sort of idea. You should, this is probably pretty clear by now, in terms of what we're doing here. And again, there's no coding at this point, there's no coding involved to use this converter. So we've basically scripted things, but you know, there is not really any coding involved at this point. And again, I'll just show a data cube, but you get the idea. I mean, you've seen enough examples. Again, so on and so forth. And the one last example I want to show you is ICR mass spec. So in this case, I deliberately chose a data cube name that's not supported by the Allotrope APIs. All of these converters can be run in permissive mode or strict mode, and that's selectable at runtime. In permissive mode, the converter automatically corrects common errors and corrects or skips non-conformant metadata. In strict mode, the converter stops on all errors and a log is written. And so basically, it's your choice at the time you execute the converter how you want it to run. The permissive mode is particularly useful during sort of a development phase, where you might expect to encounter metadata either that you haven't encountered before, or else you want to experiment with some things, you know, that may not be strictly allowed by sort of the rules. So the permissive mode can be useful in that case. And so now we're creating the ADF. Another important point I'd like to make here is that the converter framework was optimized for flexibility, not speed. Okay, still this MS dataset has over 2 million points in it, so the performance is not all that bad, considering that this really is a very low-end machine I'm running it on. I've turned the JSON off in this particular case to save a little bit of time. And like I said, this will be the last example we'll show in the interest of time. Unfortunately, because it's a over 2 million point data set, it does take a minute or so to complete the ADF construction.
Paul, could you take a couple questions in the meantime then?
Sure, I'd be happy to.
I think one of them that I've seen is how do you come up with the consensus? Is it just from your SMEs or from your internal group? How does that work?
So the consensus data model is constructed via a series of rules that we've put into the software. And so it makes them, so it's a very simplistic leaf node model or tabular model. And so what it does is it infers what the data type is, the software infers if it's a required parameter or not. And then based upon the labels that come from the file parser, that's how the pref label is chosen. So there's no scope note, for example. They're more, you know, even in the cases where they're floating point numbers, there are no units assigned. That all comes in via SME input. And so the consensus data model really is the barest bones that you can use to construct the leaf node. And then the idea is that you're going to use the SME input either from internal folks or external folks, and then ultimately the allotrope ontologies to layer on that and enrich that consensus data model. And so this is the FTMS data. And I'll just show the example here. And Explorer takes a moment because it is a fairly large data set. And lots of peaks. The one last thing I'll show here is in this case we've turned off the JSON, but we've turned on the option to create a peak table. So the software automatically creates a peak list in Excel, or it's actually a CSV file. In this particular case, there's over 10,000 peaks in the spectrum, so it's a fairly extensive list. And with that, I'd like to return to, I have a couple closing slides I'd like to return to, please. I realize we're running a little bit short, and so I'll sum it up pretty quickly. Okay, so let's go on. So again, it's a modular approach that lets us populate the ADF files asynchronously and discontinuously as needed. We can rapidly prototype many configurations with little or no coding. Once the file parser's in hand, we can turn around a new converter in a very short period of time, typically a day or two. And we employ extensive instance data checking at several places in the process to minimize the amount of post hoc validation required and to minimize the pressure to build the data shapes. Ultimately, we will build the data shapes in a separate process, but because we do a lot of instance checking along the way, we know that the data created by these files, that they're all consistent. And so the next steps, so these are all standalone converter standalone applications, as we described, that we're currently optimizing the intermodule communication. And the thought is to ultimately redeploy this network as a collection of pluggable REST microservices within our organization to support massive, rapid converter development and deployment across the enterprise. And I'd like to close with a very, very short story. I started out with a story. I want to close with a short story, again, about our friend Henry Kaiser. And this sort of illustrates, I think, the philosophy of what we're trying to do. And this was the story that was in currency, during the 1940s when Kaiser was running his shipyard. So one day, a lady visited Kaiser's office. He asked her if she'd like to christen a ship. Upon receiving an answer in the affirmative, Kaiser went to a locker, took out a bottle of champagne, and motioned for her to follow him. Kaiser then led his guests through the noise and confusion of the shipyard, eventually arriving at a quay. It contained nothing but some trash and a few puddles of water. Kaiser handed her the bottle of champagne. The puzzled lady looked at the empty quay and exclaimed, "But there's nothing there." "Never mind," said Kaiser as he looked at his wristwatch. "Start swinging." And with that, I'll be happy to take any questions that anybody might have.
Thanks, Paul. So since we're over time, I don't know if we'll be able to answer the questions on air. We should probably move on to Amnon's presentation, but thank you again, Paul, for a really interesting presentation. I know there are a number that I think have been assigned to you through GoToMeeting, so maybe you can follow up with them via text.
I'll be happy to do that, yes.
Perfect. Maybe just one quick question though. So with the converters that are being created, are they then using the APIs to write into the ADF files?
Yes, they are. Yeah, so the Pfizer
Perfect.
tool uses the Allotrope APIs to create the ADF files.
Great.
And it uses the standard leaf node pattern. So we're trying to adhere as closely as we can to the standards provided by Allotrope.
That sounds great. Perfect. Thanks again, Paul.
Thank you very much, everybody.